Welcome to ECE 302. This is lecture 5.3 on covariance. I'm Professor Stanley Chan. In the last lecture, we started to talk about joint expectations. We defined the joint expectation as the expectation of a product of x and y. If you have a discrete random variable, then this joint expectation is really the double summation of x times y, and then you multiply with the joint PMF. If it is a continuous random variable, you have x times y times the PDF, and then you integrate over x and y altogether. We have gone through the explanation of why we want to define the joint expectation as the product of x and y, and not the summation, not the subtraction, and so on. We have also defined the a ratio, which is the expectation of x and y, and then we divide it by the expectation of x squared and then the expectation of y squared, and we call it the correlation. And we also see that this is having a very beautiful geometric meaning, which is the cosine angle between two vectors. Okay, so if you recall the last lecture, we have defined it a vector x and another vector y. These two vectors, they represent all the possible states in your x random variable and y random variable. And now if they are parallel, then we say that they're correlated. If they're perpendicular, we say that they're uncorrelated. So that is what we have learned in the previous lecture. So in today's lecture, we want to go deeper into the meaning of this ratio. We want to know more about the properties of this ratio. So here is the outline of today's lecture. We will talk about independence. What happens if you have a pair of random variables and they are independent? What will happen to your correlation matrix? Okay, and we want to talk about another thing called covariance. What is covariance? Okay, we want to link the covariance with correlation. We want to understand a term called the correlation coefficient, and I want to see some properties of that. So let's start by talking about covariance first. The covariance of a pair of random variables doesn't matter if it is continuous or discrete. The covariance of a pair of random variables x and y is defined as the expectation of x minus mu x, y minus mu y. You multiply them together, and then you take the expectation. Mu x and mu y, they are the expectation of x and y respectively. So if you look at this equation, you realize that this is really not too complicated compared to the joint expectation of x and y, right? Because what is joint expectation of x, y? Well, the joint expectation of x, y, if you follow this definition here, it would be x minus 0 and then y minus 0. So instead of measuring against this mu x and mu y, just put a 0 there, that would be my my joint expectation of x and y. So this covariance is really a slightly more general version than the joint expectation. Another thing to realize is that if you replace your y by x, okay, so you have covariance of x and x. Then you have x here, you have mu x here. This is what? This is actually the variance of x. Okay, and so now you can also think about what happens if you replace the y here by x. Then you have the expectation of x squared. Okay, and is it true how you replace the y by x? This is indeed the second moment of x. Okay, so you can see that this notion of joint expectation, and then going into the joint going into this covariance, it does have a lot of connections with the one-dimensional case. In one-dimensional case, we are using the variance. In a two-dimensional case, we are calculating the covariance. If you replace one of the variables by the other, you will go back to the one-dimensional case. Okay? So this is really a generalization of the 1D case. It's called a covariance instead of a variance. Now, the covariance has a very nice property. that you can show that this covariance of x and y can be written as the difference between expectation of xy minus the individual expectations. Now, why is this true? Well, we know the covariance of x and y is really the expectation of x minus mu x and then y minus mu y. And this is the same as the expectation of xy minus x times mu y minus y times mu x and then plus mu x times mu y. And then you apply expectation to each of these four individual terms, you'll be able to get the final result, which is expectation of xy. And then if you go to here, you have this is mu x mu y, this is mu y mu x, and this is mu x and mu y. And clearly this is minus plus, so you can cancel out, so you only have one term left. Then that means you have this result, which is minus expectation of x and y. And here's actually the proof. Okay, so you can see that this is actually very, very useful. You can write the covariance using the joint expectation and also the individual expectations. There are some good properties which we can use to calculate numbers. The first property says that if for any random variable x and any random variable y, regardless whether they are correlated or not, regardless whether they are independent or not, you can always write the expectation of x plus y as expectation of x plus the expectation of y. The reason is that this expectation, this operation itself, is a linear operation. So the proof is given as follows. It's actually not too complicated, and I will expect you to be able to reproduce this proof. The reason why this is not complicated is that all you need to know is the definition of the joint expectation. Okay, so here is the expectation on x plus y. What is it? Well, according to the expectation, it would be whatever you want to calculate times the PMF. That's the joint PMF. So you plug this in, and then now you realize that you have x plus y, so you can separate them into two independent summations, one for x and one for y. Now, and then you look at these individual summations, you can see that there's a summation over all the x, but you can also shuffle the order of the summation. You can sum over the y first. Now, if you sum over the y first, what is this? This is precisely the marginal PMF in x, and therefore you get px of x. If you sum this term here, this is the marginal PMF of y, because you have sum over all the possible x, so you have py. And therefore you have this term plus this term. This term is exactly expectation of x, and this term is exactly expectation of y. Okay, and therefore you see that I'm not using any special properties of x and y, just using the fact that expectation itself is a linear operation, and I can prove this result. Now, the second property is about the variance of x and y. So if you have a pair of random variables and you take the sum of x plus y, it turns out that the variance of x plus y is by variance of x plus the variance of y. There is a very interesting term in the middle that comes out, which is the covariance of x and y. Now, of course, this covariance is not always 0. If it is 0, then of course the variance of x and y will give you just the individual variances. But since you have this covariance term here, you need to add them up. So how do we do this calculation? So we have this variance of x and y. We want to expand the term, so we have xy squared. We take the expectation, and then we subtract this expectation square. So why do we have this? Well, this is because the variance of x plus y, if you recall, variance of any random variable x is the expectation of x squared minus expectation of x the square would be outside. So that's the reason why you have the first line of the equation. Then you plug the number in, which is an expectation of so here is the square is outside the bracket. Okay, so you have expectation of x plus y, so therefore you have mu x and mu y that comes out. Then you can expand this square term. You have x squared, 2xy, and y squared, mu x squared, 2 mu x, 2 mu y, and mu y squared. Okay, so just expand all the terms and you group them. Then you can see that here you have this second moment on x, and then minus mu x squared. And then here you have the second moment y minus mu y squared, and then 2 times this term. And precisely this is the variance of x. That one is the variance of y, and this one is the 2 times of the covariance of xy. So that explains why you have this covariance that comes out. Now you may wonder, when can I have this variance of x plus y equal to variance of x plus variance of y? This will happen when this equals to 0. Okay, if this is 0, then variance of x plus y would equal to variance of x plus variance of y. Then of course we will ask, when can this happen? How can this ever happen? This happens when the 2 random variables, they are uncorrelated. Okay, so this happens when expectation of x and y equals to expectation of x times expectation of y. Okay, because what is covariance? Covariance of x and y is just the difference between these two. Okay, this is the covariance. And so if covariance equals to 0, that means this joint expectation will equal to the product of the expectations. Let's also define a term called a correlation coefficient before we come back to the discussion of this covariance equals to 0 case. The correlation coefficient is defined as the ratio between this covariance divided by the variance of x and variance of y. Now the difference between this and the cosine angle is that the cosine angle is expectation of xy divided by the variance of x and the variance of y. Not even variance of x, it would be the expectation of x squared and expectation of y squared. Okay, so now if you random variable x and y, they are not they do not have the mean of 0, then these two, of course, they're not the same. So you can see that this is like a centralized version. Okay, so central moment. This one is like just the ordinary moment. Okay, so this is defining the cosine angle. This is defining the correlation coefficient. Both are useful. Okay, now you can see that this rho has the same property as the cosine angle. It is always between minus 1 and 1. Okay, so minus 1 and 1. You can have rho equals to plus 1. That means x and y are fully correlated. If they're minus 1, that means they are negatively correlated. If it is 0, that means they are uncorrelated. Now notice that negative 1 doesn't mean that they're uncorrelated. Negative 1 means that they are negatively correlated. Okay, because if you know x, you also know y, because y will just be the flipped version of x. Okay, let us now talk about a very important concept called independent. If 2 random variables are independent, meaning that their PDF, the joint PDF, can be written as the product of the 2 marginal PDFs, meaning that you have f xy of xy, which is a 2-dimensional function, can be written as fx times fy, or correspondingly for the discrete case, you will have the PMS. Then you'll be able to get this result. Okay, what is the implication of this result? Expectation of x times y equals to expectation of x times expectation of y. This means that your covariance of x and y would be 0. Okay, So if you're independent, you will be able to get the thus, and thus will imply that the covariance is 0. Now, let me also emphasize this. Independent will imply this result, but this result does not imply independent. Okay, we'll come back to this point later. But for now, let's just try to prove this very basic result that if x and y are independent, then the joint expectation can be written as the product of expectations. The proof is actually quite simple. You go with the joint expectation, which is xy times the PMF, and then you group them. Okay, you group them as this summation over x only and summation of y only. Just group them. Now, how can you group them? Well, this is because you can write this joint PMF as the product of individual PMFs. Okay, this is true because that the random variables are independent. If they're not independent, then I'm sorry, you cannot write it this way. And once you can write it this way, then you can separate this double sum into the product of two simple sums, and then each individual one will give you their expectations, and therefore you can prove the result. This is a very important theorem. It says that consider these two statements: x and y are independent, covariance of x, y is 0. This implies that, this doesn't imply that. Okay, or let me just put a box here. Independence would imply uncorrelated. Okay, because if you're independent, then you can make the expectation of x and y equals to the product of expectations. Okay, and therefore the covariance will be 0, and therefore it is uncorrelated. Now, if you start with this covariance equals to 0, or meaning that your joint expectation can be written as a product of expectations, that does not mean that your PDFs, the joint PDF, can be factorized into a product of PDFs. Okay, so this is a much stronger condition. Having this, you'll be able to prove that, but having that, you cannot prove the other one. Okay, and therefore independent would imply uncorrelated, but uncorrelated does not imply independence. Now, if you are ever interested in proving these two results, the first one is already proven here. Okay, if you're independent, you will get uncorrelated. The reverse direction, all you need to do is to come up with a counterexample, meaning that you can construct a pair of random variables that are uncorrelated, and then you can show that they are indeed you cannot get them to be independent, or meaning that you have a pair of random variables that are uncorrelated, however they can still be dependent, and that is possible to construct. Now, for the details, you can check our ebook, and there's a very concrete example to show you this counter argument. Now, finally, I want to comment on how do you actually compute the correlation coefficient in practice, and what kind of implication does it have to you when you try to do data analysis. Remember that the correlation coefficient is defined as this joint expectation minus the mean divided by the standard deviation or the variance. Okay, each individual term in this definition can be approximated by your data set. So when I say this, I mean that you have two random variables, x and y. You have a data set that contains x1, y1, x2, y2, and so on with xn, yn. You have many these pair of random variables. Okay, so you can compute this expectation, which is this summation. Okay, summation of x times y, and divide by all the number of samples. That's just the average. For the denominator, you have sigma x, which is the square root of this variance. Okay, and then here you have sigma y, which is the square root of the variance of y. All these can be calculated on computer. So you will be able to get a quantity which is like this. This is what we call the empirical correlation coefficient. It is completely determined by your data set, and it has the exact same form as the formula that you have here, although this is a theoretical one, this is the practical one. You can plug this calculation into the data sets as follows. Suppose you have a data set that has this kind of distribution, you plot them into two-dimensional space. You can calculate the correlation coefficient. You can get a number of 0.0038. What does it mean? Well, it means that the random variables x and y, they are almost uncorrelated because the correlation coefficient is close to 0. And you can see from this diagram, it is indeed the case. By knowing one point in the space, I almost have no idea of what would be the likelihood to get the other variable. So for example, I have x being 4. I can have a variable that takes a value of -1, or I can also have a value that takes a number of 1. I can even have a value that takes a number of 3. I just don't have any clue about what my other random variable would be by knowing one of them. In the other extreme, let's say here, you calculate the correlation coefficient, which is almost close to 1. Then by knowing that one variable is taking values of 4, you're almost certain that the other random variable will take the value of 4 as well, which is because they are correlated, right? And so the correlation coefficient will tell you how much correlation are there between these two variables. It could be that when you're running a regression analysis, you have two sets of variables. One could be the age, the other one could be some other variables. You want to see if there is any correlation. And then you plot this correlation coefficient diagram, you plot all the data points, you calculate the correlation. You can see that, okay, there is indeed a trend or there is no trend. So that can help you do some very meaningful data analysis. So I hope this lecture has given you some very practical and useful knowledge about calculating the relationship between two random variables. You can calculate the covariance. You can also calculate the correlation coefficient. The covariance is really a generalization of the variance. And the correlation coefficient is really another version of the cosine angle that we have talked about in the last lecture. One very important thing to remember in this lecture is this one-sided relationship, that independent would imply uncorrelated, but then uncorrelated does not imply independence. So I hope you will be able, you'll be able to differentiate the concept between the two. This is the end of this lecture. I hope you have learned something. If you have any question, please let me know. Please post your questions on our Piazza forum, and I will be very happy to answer your questions there, or you can send me an email. I'll be happy to answer your questions as well. Thank you very much.